Complex numbers. The name itself sounds, well, complex, right? It sounds a little intimidating. But what if I told you that adding and subtracting them is actually based on simple algebra you almost certainly already know? Let's jump in and see just how surprisingly simple this whole complex thing really is.
So first things first, where do these numbers even come from? Well, for a long time, mathematicians were stumped by a pretty basic question. What's the square root of a negative number? I mean, there's no real number you can multiply by itself to get a negative. So they did what mathematicians do best. They defined a solution. They basically invented a new number, called it I for the imaginary unit, and give it one simple job, to be the square root of -1. And just like that, problem solved.
So think about it this way. You've got all the numbers you use every day, right? 5, -17, pi. We call those real numbers. And now we have these new imaginary numbers that use I. Well, it turns out they both just belong to a bigger, more inclusive family, the complex numbers. A complex number is really just any number that has a real part and an imaginary part put together.
Okay, so we've got this whole new category of numbers. But what can we actually do with them? Well, this is where things get really interesting. This is where numbers literally break free from the simple number line and pop into a whole new dimension. This is what they look like in their standard form. Every complex number has a real part, we'll call A, and an imaginary part, BI. Now, the most important thing to get right now is that these two parts are totally distinct. You can't just mash them together into one number. They live side by side, and that separation is everything. And that brings us to the big secret of this entire operation, adding and subtracting complex numbers. It isn't some brand new, scary kind of math. Nope. It is built on a skill you already have down pat. Just take a look at these two problems. On the left, you've got a standard algebra problem with a variable t. On the right, a complex number problem. Do you see it? The structure is exactly the same. And if they're structured the same, that means you should solve them the same way too.
And that's it. That is the big reveal. You don't need to learn a new set of rules. All you're doing here is combining like terms. You take the real parts and put them with the other real parts. You take the imaginary parts and put them with the other imaginary parts. Seriously, that's the whole game.
All right, so let's put this into practice. Let's get our hands dirty and actually walk through the mechanics. You're going to see just how clean and simple this really is.
The process is always the same, just 3 easy steps. First, you just pull out all the real parts and stick them in one pile. Then, you do the exact same thing for all the imaginary parts, put them in their own pile. And finally, you just do the basic addition or subtraction within each group. Simple.
Okay, let's try one. We have 3 plus 7i plus -6 plus 8i. So let's group our like terms. The real parts are 3 and -6. Together, that's -3. The imaginary parts are 7i and 8i, which gives us 15i. And boom, there's our answer, -3 plus 15i. See? Not so bad.
Now, a quick heads up for subtraction. There is one little trap that people fall into. As the folks at Radford Mathematics point out, you've got to be really careful with your signs. A great pro tip is to always use parentheses when you subtract. It forces you to distribute that negative sign correctly to both parts of the second number.
Let's run through a subtraction example. So for the real parts, we've got 4 minus 8, which gives us -4. And then for the imaginary parts, it's 3i minus a positive 2i, which just leaves us with a single I. So our final answer is -4 plus I. Done.
Okay, so we've nailed the how, and it's way simpler than you might have thought. But this is where it gets really cool. Let's talk about the why. Why on earth do these real and imaginary parts have to stay separate? The answer is going to give us a completely new way to picture what numbers even are. I mean, this is the question that unlocks the whole idea, right? If it works just like algebra, and we can combine 2x and 3x to get 5x, why can't we just combine 2 and 3i? Well, it's because they aren't just different terms, they represent completely different dimensions. And this is why. Check this out. It's called the complex plane. Think of it like this. All the real numbers you know live on the horizontal axis, just like a normal number line. But the imaginary numbers, they get their own axis, the vertical one. So a complex number like a plus bi isn't just a point on a line. It's a specific address on a two-dimensional grid.
So if a complex number is really just a coordinate on a plane, we can also think of it as an arrow or a vector pointing from the center to that coordinate.
And if complex numbers are like vectors, it stands to reason that adding them should work just like adding vectors.
And look at this. This is what happens when we add them visually. To add vectors, you just add their x parts and their y parts separately. Well, that is exactly what we were doing with the algebra. We added the real parts, the x-axis, and the imaginary parts, the y-axis, separately. The rule we learned, combine like terms, isn't just some random rule. It's the algebraic description of this picture. It's the same logic.
So, okay, the math is beautiful, it's elegant, but is it actually useful? Oh, you have no idea. Let's take a look at how these supposedly imaginary numbers are absolutely essential to building our very real, tangible, modern world.
It is pretty incredible to think that the mathematician who first dreamed them up, Girolamo Cardano, he just dismissed them. He called them fictitious, like they were just a useless little mathematical quirk. He had absolutely no idea what they would one day become.
Fast forward to today, and in engineering, complex numbers are everywhere. I mean, take electrical engineering. The flow of AC current in your walls has both a strength and a timing, or phase. Guess what? A single complex number can describe both of those things perfectly. They're also critical for analyzing signals and in control theory, making sure that things like a plane's autopilot system stays stable and doesn't go haywire.
And their role in physics is even more mind-bending. At the quantum level, it seems like reality itself needs them. The famous Schrödinger equation, which is fundamental to how we describe the quantum world, it just flat out doesn't work without the imaginary number I. They're also used to make calculations in electromagnetism and even relativity way, way simpler.
And the list just keeps going. They help us describe how water flows. They're used to analyze the vibrations in huge structures like bridges and skyscrapers. They're even used in cartography, in map making. They are truly the hidden mathematical engine powering so much of our society.
And that brings us right back to the beginning. They started out as a fictitious answer to an impossible question, but now they're one of the most powerful and practical tools in science and engineering. It really makes you stop and think, doesn't it? What other imaginary ideas that we have today are going to build the reality of tomorrow?